So hi everyone, I'm Sinu. I work at PSE at the Ethereum Foundation. Every once in a while we put on some of these learn and shares. Sometimes we have a guest. Today we have Carsten Baum. He's an associate professor at GTU Compute in Copenhagen, Denmark. And his research focuses mostly on efficient post-quantum secure computation and zero-knowledge proofs. There's increasing attention on quantum risks and therefore more attention on PQ proof systems, and Carsten's going to talk about one such construction today. In addition to also being PQ, these VOLE constructions are also really compelling in terms of like their end-to-end performance, and so they're really interesting for privacy-preserving client-side proving applications like digital identity and such. So I'm trying to encourage people to look more into them, and yeah, so I invited Carsten over. And he's kindly accepted. So I'll pass it over to him and I'll let him do his talk.
Cool, thank you. And thank you for the, of course, for the invitation and for the kind words for the introduction. And yes, what I will talk about today, these VOLE-based ZK proofs, they have quite a few applications in the area of digital identity. Funnily enough, last week I've been at the Real World Crypto Conference in Taipei and actually talking to quite a few people about applications to privacy-preserving digital identity, that being VOLE-based constructions or others, and what the future will look like. And it seems that there's a lot to be done. So I'll try to explain how they work. They are not as complicated as you might think, and I'll try to explain a few applications. Yes, and as Sina just said, if you have anything that you want to ask, just raise your hand, and we'll do this just a bit more interactively. Yeah, first of all, before I will go into technical details or anything, just that this whole this presentation is based on quite a few works by now. Have appeared at multiple conferences, and so there's a fantastic large set of co-authors that I of course want to thank. Yes, there's NIST specifications in there. There's publications in there that led to all of this. And what I wanted to do is first explain how these proof systems work. What is a VOLE? What are VOLE-based proof systems? How is VOLE-in-the-head working? And then two applications. One of them is a post-quantum digital signature scheme that is currently in the NIST process for these like additional on-ramp signatures. Will it be standardized? I have no idea. But I think it's kind of cool, and I think people find it interesting just design-wise. And it was like kind of the first application that we found of these VOLE-based proofs, VOLE-in-the-head-based proofs. Then I'll talk about blind signature scheme, which is some recent work that will appear this year at Usenix Security, one of the top conferences in computer security. And blind signatures are probably something that everybody in the cryptocurrency space is familiar with. I mean, the old way of doing digital cash before Satoshi came around the corner, for example, was using Charm's blind signatures. So this kind of stuff is probably of interest. So if you look at your zero knowledge proofs, then the way how it's usually discussed is in two terms: the proof of runtime, proof size, and if you do any kind of engineering, there should be a third axis, which is how hard is it actually to implement this thing. I leave that out here and just focus on proof of runtime and proof size. Usually, if you have a larger statement, then if you want your proof size to stay rather small, you take a succinct proof system such as Ligero, Starks, or however they are all called. They have a succinct proof. At some point, the proof is smaller than the statement that you're trying to prove, but they all have this disadvantage of having a proof of runtime that scales non-linearly in the size of the proven statement. So your runtime increases quite a bit over just running the actual computation that you want to prove. So these have these are often interesting if you are in a blockchain context. If you think about having a proof that is smaller than what you're actually trying to show there, and also a verifier runtime that is very small, if you want to do ZK rollups or so, for example. But then there are also quite a few applications where the proven statement is actually quite small, and you pay a lot for the succinctness. These are proof systems that, and they're usually proof systems are interesting that have a proof size that is larger, even up to linear in the size of the statement that you're showing, but where the prover runtime is quite a lot smaller, right? So where the overhead that you're paying for proving something in zero knowledge is like the concrete cost of doing this is small enough, but it gets you a proof that is larger, and the verifier runtime that is larger. But in cases like digital identity, this is often fair enough. And the state of the art there was MPC in the head for a long time, among other proof systems, and then recently VOLE-based zero knowledge came as another solution to that. And here I mentioned only proof systems that are post-quantum secure. So of course there's a lot of you can do a lot with elliptic curves and pairings, but I don't mention that here because I only care about the post-quantum setting. And in VOLE-based ZK, we can actually, or for proving circuits that are binary circuits, we can get as small down to 1 bit of communication per AND gate that we have in the designated verifier setting. So that's kind of the best we can hope for. And there's been a lot of work in optimizing this kind of stuff. So how do these proof systems actually work mathematically? They are quite simple. And what we need for them to work is a bit of an understanding of what is a vector oblivious linear evaluation, or a VOLE. And in the VOLE, you have a correlation between the prover and the verifier. So the prover has some information, verifier has some information. The prover in this example here has a vector u and it has a vector v. They usually can both of them just be random. And the interesting part is that the verifier also gets some information, which is delta, that is some random field element, and then a vector q. And q is the fun part, because q is actually a linear combination of the vectors that the prover got. However, the linear combination is such that one element, namely u, is multiplied by the scalar delta that the verifier also has as information. So you have vectors, everybody there gets vectors except for the scalar delta, and you're kind of evaluating a linear function which has the one element u, and in this so if you think about this, you could think about q as being kind of the evaluation of a polynomial determined by u and v that you evaluate in the point delta, right? So you could think about this as the prover getting a polynomial of degree 1 or a linear equation, and the verifier getting the evaluation of this linear equation in a single point. So it knows the point, and it knows the evaluation of this polynomial in that point. This is what a oblivious linear evaluation is. And if you do that for a lot of linear equations in the same that you evaluate in the same point, you get a vector oblivious linear evaluation, or a VOLE. This is what these things are. And that's kind of the most. Oh, I see a hand being up. Hi, Justin. What would you like to ask?
Hi there. Just a quick question. In practice, are there any constraints on the field? Does it have to be of a certain size to be cryptographically relevant? Does it have to be a prime field or anything else?
Fantastic question. I have been sweeping a lot of things under the rug here. What you usually want is that your field size is large enough to like something of the size like 128 bits or so. However, you can arrange things such that, for example, u is only going to be in a subfield. For example, it's just a bit, and everything else is in an extension field. And that turns out to be nice, because that allows you to do efficient proofs. Later on, that allows you to do efficient proofs where you just send 1 bit but you get soundness that is as large as the security parameter. But yes, good question. Thank you. And yes, if there's anything else, just hands up. Okay, where were we? So we have linear equations, and we want to we evaluate them. And Justin has another question. Yes.
Sorry, I got confused. I was trying to put my hand down, but I accidentally put it back up.
Okay, so no question. Good. Then I'll continue. So yes, so we have this setup. On one side, the prover has U and V. On the other side, the verifier has the evaluation of this linear equation. What are we going to do with this? The interesting thing is, this is already a linear commitment, and this has been known since like the ages of the ancient ages of cryptography. Maybe not the old Greeks, but since the 1980s for sure. Because like if you have this correlation that commits the prover to the value U. It also commits it to the value V, but let's for now think it's the value U. Well, why is that? If the prover, so if you think this is a commitment, so the verifier has Q and delta, the prover can open it by basically sending the equation to the verifier, and the verifier can check if when he evaluates this equation on the point that he has, that he gets Q, so the evaluation of that point. So that's kind of the opening of the commitment, and it reveals the message U. This is hiding because at no point does Q or delta leak any information about U before the prover actually opens them. Right? There's like if you let V be uniformly random, when you generate these VOLE correlations, then nothing about U is being given to the verifier. And at the same time, it's also binding, and this is just like good old Schwartz-Zippel as it's been using everywhere. If I don't know the point at which the verifier has the evaluation of the polynomial, the moment I use a different secret, I get a different polynomial, and that's only going to agree with the polynomial I started with in one point, because two lines, if they are not identical, only intersect in one point. So if you, as the prover, you don't know delta. So if you change your opinion about U, you're very likely getting caught by the verifier, except with probability 1 divided by the field size, which means that this is actually a commitment. And since if you add two equations, you get another equation of the same degree. This is also a linearly homomorphic commitment. So this just the kind of the dumbest way of doing commitments. It requires that you're able to generate these VOLE correlations to begin with, and that's what most of the research has been about. So yes, this is something we already observed back in 2021 to build an efficient proof system in the designated verifier setting, where delta is being kept from the prover. So how do you build a proof system out of this? If you have random VOLEs that are commitments to random values, you can de-randomize them. You can, it's a linearly homomorphic commitment scheme. So as a prover, you can just announce the differences between what you want to commit and the secrets that you actually want to put in there, and what is committed there right now. And this allows you to update the commitments to something that you actually want to have. And then you use the linear homomorphism to evaluate the circuits. So you can add commitments because they're linearly homomorphic. You can multiply them using a multitude of different techniques. That's actually where most of the research has been in. And then at some point, you get the output, a commitment to the output of the circuit, and then you just open a commitment. Like this is kind of standard techniques as they are used in many zero-knowledge proof systems. And it's usually called the commit and proof paradigm. That is also, at this point, almost as old as me. Yes, so that's what you do. The thing about vectorial E-based proofs is that you're usually not looking at them just as commitments and addition and multiplication gates or linear gates. Instead, the programming model for them is quite different, and that's what I want you to think about, because this is actually important to how you use them. Usually you care in the ZK proof system about how many multiplications you do, because this directly impacts the communication that you pay for. In VOLE-based proof systems, this is a bit different. You could think about it as follows: every wire in your circuit has a degree, and your in degree is actually 1. So because you start with commitments that are of degree 1, linear equations, so to say. Now, whenever you do an addition or a multiplication, you either keep this degree of your commitments going in, or you increase the degree. So, for example, if you do a multiplication, instead of getting a commitment of degree 1 out, you get a commitment of degree 2 out. So a degree 2 equation, and so on and so forth. And that makes the degree grow throughout your circuit. And at some point, you can use what I would call a reduce gate that allows you to get the degree down to 1 again. The interesting thing is that if you look at what is the cost of evaluating a circuit based on commitments in the VOLE setting, then actually both linear and multiplication gates are for free. Like, they don't require communication, but multiplication gates increase the degree. And then you can have a gate that reduces the degree again, but then you actually have to pay for the communication. So that is kind of the programming model that I have in mind. Now the obvious question that you would ask is, why would I ever do a reduction of a degree? Well, the thing is also that the prover computation time depends on the degree of the commitments. So this means that in VOLE-based zero knowledge, you have an interesting trade-off between in how you do multiplications, for example, in that you can increase the prover runtime and make the proof shorter, or you instead want to like make the prover runtime as optimal as possible, but then you're fine with a communication being larger. But since communication also always entails delay, there's actually an interesting trade-off to be found there. So that's just something for you. I want you to keep in mind when we look later on at applications such as digital signatures and blind signatures. So now everything I've been telling you about was that the verifier keeps a secret state delta. And that's not really great if you want to build non-interactive zero-knowledge proofs. And often we want to have non-interactive zero-knowledge proofs, right? We want to just be able to send a proof to somebody else, and then they verify it, and they don't need a secret state for that, because otherwise proofs will be not so sound if the prover ever gets the secret state of the verifier. So how can we get rid of this? And this was actually something that we looked into in 2023, and we came up to the following conclusion. Well, let's look at these VOLE-based proofs and how they are working. So in the beginning, we want that the prover gets his or her linear equations, and the verifier gets the evaluations. The prover also has her witness that she wants to prove something about. Now, in order to generate the proof, in order to generate the zero-knowledge proof, the prover needs her share of those linear equations. So she needs U and V. She needs this information in order to generate the proof that she then sends over to the verifier. Okay, so she runs, she commits to the witness, she does the circuit evaluation, blah, 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 blah. That at no point does that actually need, does the verifier at this point need anything from those VOLEs, from those VOLE correlations so far. Like, there's just no interaction that would where he does anything based on those VOLEs. So until now, the verifier could actually have been silent, except for sending random bit strings as challenges in the ZK proof. And now we're in the situation where the verifier would like to verify. But he hasn't gotten Q and delta yet. So what are we going to do? And the interesting thing is, at this point, the prover has now finished her whole proof, anything that is based on U and V, and so on and so forth. and she can't, like, if she does learn delta at this point, this is not of any help anymore, right? She has finished her proof. The only thing she can do is not give the we could take her help in giving the verifier his share, Q and delta, as long as this is correct, right? She can't convince the verifier of the wrong thing anymore, of a wrong proof. Like the soundness of the proof is ensured. She can learn delta. So let's do that. The verifier will give her delta, and she will give delta. She will give Q to the verifier as long as the verifier can verify that it's the right Q. So actually, in VOLE-based zero knowledge, what I said earlier, that we want the soundness, that the proof is sound because the prover doesn't know delta, is actually not right. The proof system is sound as long as the prover doesn't learn delta before he finished, or before she finished the whole proof stuff, right? So afterwards, she can learn delta, and anything is still okay. But there's now an asymmetry where the prover learns some information a lot earlier than the verifier, and this actually is something that we can use in order to build a proof system that is non-interactive, right? Because there's no secret state that the verifier has anymore that would make it necessary to be a designated verifier proof. And this is actually how VOLE in the head works. So let's put the VOLE into the head, and I think ChatGPT or whatever for generating this picture a long time ago. How do we actually now make the proofs publicly verifiable? Well, first of all, this has a downside in the sense that, of course, we're linear sized. VOLE-based proofs are also linear sized. That was what I mentioned before, but they will now have a larger overhead in comparison to those designated verifier proofs. You pay something for mod 2, for binary circuits, you pay 11 to 16 times the witness size. However, you can compress multiplications again, so it's not actually what you pay. But the cool thing is the way how it's set up is that we only use AES and SHA in order to build these VOLs, to generate these VOLE correlations and do the whole proof, which then makes the implementation quite efficient. And as I said, throughout the rest of the presentation, I'm going to talk about, well, like, how do I turn this into a signature scheme, and how do I turn this into a blind signature scheme? And the way how to think about this is, well, I want to generate VOLE correlations. How will I do this? And if you have ever heard of something called oblivious transfer, there's actually a nice way of getting VOLE correlations due to Lance Roy, paper from Crypto 2022, where he observed, well, if I have secret sharing, I can build VOLs over kind of the same field of size n. And it works as follows. I take my U, so this is the secret from my VOLE. I share it into n individual pieces, so if I add them up afterwards, I get U back. And now I run an n-1 out of n oblivious transfer, so I give n-1 of the n values UI to the verifier. Then I can think about this as being equivalent to picking a delta in the field and obtaining all UI where I is not delta. This is what an n-1 out of NLT is doing. So it gives me everything except the index, except a certain index, and that is the same in this case as getting all UI that are not I being the index. Okay, well, how the hell can I turn this now into a VOLE? Here's the interesting observation. Well, as I said, my U is the sum of all the individual shares. Now, this is fine. The interesting thing is, how do I define V? V is this odd here. If you see it on the lower left side, is this odd a sum where I'm not just summing the UI, I'm actually multiplying them with minus their index. So -1 U1, -2 U2, -3 U3, down to -n UN. This is how I define V. Okay, so I have U and V that my prover needs. Now I just need to make Q and delta I've also already chosen, how can I derive Q from this, right? If I have this linear equation defined by U and V on the left side, how can I get Q on the right side based on these n-1 values? And the thing that Lance observed back in 22 is the following. It's really trivial, but it's great. So what if I sum up all the UI that I got as the verifier, and I multiply them with delta minus I. So on the right side here that you see, you have the summation of all the UI multiplied with delta minus I. Well, delta minus I is going to be 0 when I equals delta. So I can compute this sum Q as the verifier, even though I'm missing a single UI value. So that's great. But at the same time, if you expand this equation, this equation is actually U times delta plus V. Even with as the verifier, even without having UI at this specific point, I can still evaluate the polynomial in the point delta by just setting things up in this way, as I just mentioned. And that is how from n-1 secret shares I get an OLE correlation and a VOLE correlation. Okay, now oblivious transfer is an interactive primitive, doesn't allow me to build a non-interactive zero knowledge proof. But how do we then turn this into a kind of into a VOLE generation for a NISIC is, well, instead of kind of generating n secret shares and sending them through an OT, and the receiver only learns n-1, what I can do is I can commit to n bit strings, n random strings, wait for a challenge from the verifier, and then open all except one of those bit strings. So an all but one vector commitment. And those things we know how to very efficiently do in a post-quantum setting based on pseudorandom generators. And then, as I said, then with this, you just convert them to VOLE locally. But the great thing is the prover has all the information she needs in order to generate her share at the time when she generates the commitment. And the verifier, only needs to ask for the opening at the time whenever he actually wants to verify the proof. Okay, so how do we do such an all but one vector commitment? It's actually very simple. You take your favorite pseudorandom generator like AES encounter mode, and then what you do is you pick yourself a seed, a random seed. You apply the PRG, and now you recursively apply the PRG again and again and again. Right. So that just gives you a tree. That's usually called the GGM tree. And yes, so this is how you expand, how you generate all of the random values that you add together in order to generate the VOLE correlation. In order to commit, you just hash them together down as a Merkle tree. That's all fine and good. And then how do I open all but one of those values, right? If somebody wants to give you all of these PRG seeds except for one, well, you can look at the path from delta to the top that generated everything, and you now simply reveal everything, all those intermediate nodes on the tree that are kind of on the co-path of this, right? So whenever you go down like a level, you look at like what is the sibling node to the node that is on the path, and you reveal all of these. So in order to reveal n-1 leaves, I only need to send you log n seeds, right? So this is how I can build a lot of. So this is how I get all of these PRG seeds to somebody. And now what you can think about is for my VOLE correlations, I can generate random I can generate random VOLEs just by giving the seeds to you, and now you can locally expand them into arbitrarily long strings. So if I give you the seeds on the bottom here, they just define arbitrarily long VOLE correlations that are random, and then you just need to de-randomize them. There's actually optimizations for this kind of stuff, because it turns out that this can be expensive if you do a lot of this. But this is a way of setting up VOLE correlations that we use in VOLE-in-the-head. You then need to de-randomize them, which is where this overhead 11 to 60 comes from. Okay, so far about like that technical part of it. Then, so we saw a way of how to generate these VOLE correlations, and then we saw if we have VOLE correlations, we can just simply turn them into a zero knowledge proof. So that we have. Now let's use it for something. I'll start with digital signatures. This is probably the digital signature scheme with the worst logo that has ever been invented. We did a terrible job in Paint there, but now we're stuck with it. What we did there was we used the following observation, which is not just to us. Other people have been thinking about this before. Well, if you have a non-interactive zero knowledge proof and the one-way function, then you actually easily can build a digital signature. How? Well, you pick your one-way function, evaluate it on a random point. The output of the random point, the output of the one-way function evaluation becomes the verification key, and the input is the secret key. How do I do it? The signature. Well, I prove in zero knowledge that I know the secret key that evaluates to the verification key. And then you use your usual Fiat-Shamir transform to hash in the message, and whoops, out comes a digital signature scheme. But this is all fine and good. But as you can see here, it requires that we prove in that we evaluate the one-way function in zero knowledge. So that means the signing time of my digital signature scheme is going to be proportional to the runtime of a proof of knowing a pre-image of a one-way function, and the signature size is going to be proportional to the proof size. So for VOLEs, that means, for VOLE-based decay means, I want a one-way function that I can easily express in the circuit format that I mentioned to you earlier, and then that directly translates into the proof size that you're getting. So you could look at your most favorite like let's take an encryption scheme as the one-way function, where you fix an input. The secret key of the encryption scheme, some kind of block cipher, for example, becomes your secret signing key, and then you like the encryption of a publicly known input using this secret key is your verification key or your public key. This has been used in a signature scheme called Picnic before. So this could be an interesting starting point. And now you could think about, okay, let's take any kind of zero knowledge friendly encryption scheme and use this as the one-way functions. There's stuff like lowMC, MIMC, Poseidon, rescue, all these kind of hash functions. I looked into that and then had an interesting thought, which is, why not AES? But if you want to build a digital signature scheme that you want to be conservative, you probably want to use an encryption scheme in there that is as battle tested as possible. And say what you want about Poseidon and all these other ciphers, but everybody has a bit more is a bit more convinced about AES than other encryption schemes, and we're already using it as a pseudorandom generator in order to generate these VOLE commitments. So let's just use it. So we looked at AES, and can you actually run AES efficiently in a ZK proof system? Usually people say no. So what we looked at AES again. Let's quickly consider how it works for a 128-bit block size and then key length. Well, first you have your key expansion, which expands your secret key into a number of round keys. Then you XOR your incoming message with the first round key. That gives you the initial state. You apply the round function, which includes throwing in the next key from the key expansion, you get the next state, you repeat the whole thing for 10 rounds, and out comes the outcome of AES. So that's evaluating AES in plain. So if we wanted to use it as a one-way function for digital signature, we would have to do all of this stuff that is displayed here in zero knowledge. So let's leave out the key expansion and focus on evaluating the round function. So what is the round function in AES? Well, it has a nonlinear part. This is unsurprising. A block cipher that is only linear is not very secure. But so it has this nonlinear part called subbytes, the S box of AES. But then in addition, it has these other three steps: shift rows, mix columns, and adding in the round key. And they're all linear operations. And if you think about it from a ZK proof system perspective, if you commit to the state and if you commit to the round key, right, applying linear transformations is, linearly combining commitments, which is for free, right? This is prover runtime, but this is not communication. And since we care about getting the signature size or the proof size small, that's great. So we have to think about how does the S box look like. And interestingly, the Rheindal or AES designers back in the late 90s, early 2000s, did us a great favor by designing an S box that is actually very, very, very nice if you want to evaluate it in a ZK proof. Because what the S box in AES is doing, it's inverting, it's looking at the input bits. It takes 8 bits and maps it to 8 bits. It takes these 8 bits and looks at these as being an element in a field, like some version of f2 to the 8. And then it inverts this element in the field, and that's the output of the S box. It maps 0 to 0, just so we're complete, but this is how the S box actually works. And now if you're like me, then you realize, well, in ZK, I know what the input and the output is. So to check that the S box has been correctly evaluated, I just need to do a multiplication in f2 to the 8, and multiply the input and the output, and check that it's 1. Right? This is how I figure out that an S box has that I get the inverse of the input is if I multiply the 2, and it gives me 1. Okay, now an input could be 0 with probability 1 divided by 256. For the first version of FAEST, we actually just assume that it never happens, which reduces the key space a little bit. For the newer version of FAEST that we have now published, we actually handle those cases as well. Okay, so then how you actually check evaluation of AES as a NISIC, as a VOLE-based NISIC is the following. You commit to the states of every round as bit commitments. Then you apply the linear function, add the round key. All of this is committed to over f2. These things don't cost you anything in communication. You had to commit to the states that was necessary, but then to evaluate the linear functions forward and backward from the state, you pay nothing. Then you can, in VOLE-based proof systems, actually lift your secret from a base field to an extension field. So your committed value can be lifted to an extension field, in this case f2 to the 8. And then I can do this check over f2 to the 8, this check that it's actually an inverse. And I only have to do like one multiplication for it. So this we turned into this again is actually a full-blown non-directive zero knowledge proof system, which we implemented, and it got us around 5,000 to 6,000 bytes for a signature, and then sign verify times up to 4 milliseconds. So that was FAEST round 1. Then we threw in a lot of optimizations for optimized GM trees, optimized AES evaluations, and so on and so forth. And we could actually squeeze the signature size down to 4,500 bytes approximately, and sign and verify times that are down to the 500 milliseconds microseconds, so half a millisecond. Now we would have to set this into perspective. This is a sign and verify time that it's equally good for an optimized MLDSA, for example. We get worse signature sizes than MLDSA, which would be the standard that you have for post-quantum signatures. However, we don't require any lattices for signatures. We just use AES and SHA. So that's it, right? So that's your hardness assumption there. So that is an interesting trade-off. Anyways, as I said, we have a signature that is but it's actually a full-blown non-interactive zero-knowledge proof system. So what else can we do with it? And one thought that we had was, let's build a blind signature scheme out of it while we're at it. What is a blind signature? The way how it works is you not just have a signer and a verifier, you have a signer, a user, and a verifier. So the user has a message. The signer generates the signing key and the verification key. It hands out the verification key to everybody who wants to have it. And now how do you sign? Well, you have an interactive process with the signer who gives you the signature, and then you can show the signature to anybody out there. As a user, you can give the signature to other people. Now, why is this an interesting cryptographic notion? Well, first of all, we want it to be a signature, so the user doesn't have the signing key, so the user without interaction with the signer can't sign messages. But more importantly, the signer also never learns the message. So the signer really kind of generates, really signs a bit string without having any clue what he's signing there. This has numerous applications in digital cash, but also in rate limiting and other applications. Okay, those are blind signatures. These are signatures, but like with a little more, one could say, right? So, and one thing that I also have to throw in, if you want to build a digital identity scheme that is privacy preserving, also called anonymous credentials, you usually start by building a blind signature, and then you extend it to an anonymous credential. So building a blind signature is also actually the starting point of building a full-blown digital identity system. The way how blind signatures can be built, there's like a well-known construction due to Mark Fishlin from around 20 years ago. How does that work? Well, you have your signing key, verification key, same setup as before. Verification key is known by anybody out there. The user, what does the user do? It hashes or it commits to the message together with some randomness and sends the commitment to the signer. It can just be like a hash of the message padded with some randomness. Now, the great thing is this will not reveal any information about the message to the signer because it's a commitment. The signer signs the commitment and returns it together back to the user. So the user gets a signature on this commitment H here. And now what is my blind signature? My blind signature is a zero-knowledge proof of knowledge that I have randomness and I have a digital signature such that if I compute the commitment function on my message and my randomness, I get a commitment string out, namely H, and I have this digital signature. But since it's a proof of knowledge, it actually keeps sigma and R private. So as a verifier, I don't learn the commitment and I don't learn the digital signature. Right? Instead, I only get a proof of knowledge of a signature. But this proof of knowledge is in itself kind of the proof of knowledge of a signature is in itself a signature. This was kind of an idea that Mark Fishlin had back in the middle of the 2000s, and this is a well-known design for blind signature schemes. The great thing is it works for any kind of blind signature of any kind of signature scheme that you can throw in there. So if you take a post-quantum proof system and a post-quantum commitment scheme and a post-quantum digital signature scheme, you should get a quantum secure a blind signature. And if your verification function is very efficient, When evaluated in ZK, then you actually also get a very efficient blind signature, because again, the size of your proof is the size of your signature. The runtime of the NISIC proof is the runtime of generating a blind signature. What we're going to use here are, as a signature scheme in our construction, are I'll leave out this part, are so-called Mayo signatures. How do they work? In Mayo, or in unbalanced oil and vinegar, what you get as a public key for a signature are just a bunch of matrices, random-looking matrices, M1 to Mn. That's how they're called here. And what is a signature? Well, you hash the signature on a message you generate as follows. First, you hash a message that gives you a vector, and the vector is as long as the number of matrices Mi that you have. And then your signature is actually a solution S, such that S times Mi times S gives you all these Vi values. So if I take the same vector S and I multiply it in the right way, left and right, with all of these matrices, I get out V. So I have to solve a system of quadratic linear equations to generate this S vector in order to generate this V vector. So verification here is first of all, signing is very complicated. You need that these matrices are formed in a certain way so that you actually can solve this system of quadratic equations, because normally it should be computationally infeasible to actually solve it, or solutions should not exist. But the trick is that you set up these matrices in such a way that you can easily find such a pre-image S using what is called the oil space of these matrices. That's where all the hardness on designing the signature schemes is in. The great thing is, in order to verify that you have such a signature, well, you just have to multiply a publicly known matrix, namely your public key, on the left and on the right with a secret vector, and compare it with the hash of the message, and there you go. Right, that's your verification. So it's just a quadratic equation that you have to evaluate and compare with the hash of a message. And actually, that's what we took as a starting point, and that's how we built a blind signature scheme. So the first thing we did was we really took what Fischling did and squeezed it into VOLE-in-the-head. For that, we have to run shake or SHA-256, no, SHA-3 on the public message, and we have to evaluate it inside zero knowledge. And usually, if you ask any person who designs ZK proofs, they tell you, please never hash with shake inside the ZK proof. That's what special ZK-friendly hash functions are for. But it turns out that with some massaging and actually with the fact that we use VOLE-in-the-head, this is very ZK-friendly. In the same way as with AES, we looked at how shake works, and shake works by basically applying a permutation a few times. Basically, this consists of 24 individual rounds, each of these permutations, where some part of it is linear and invertible. So this is easy to compute if you have commitments to each of the individual bits. And then you have a degree 2 function. And we were, since it's a permutation, you can also compute it backwards. And backwards, it's degree 3 for each of these 24 rounds. And then with some playing around with how you build a circuit for this specific for shake, we were then actually able to, instead of having to commit to all 24 rounds of evaluating shake, we only had to commit to 4 of the intermediate rounds. And then we use these tricks of being able to multiply efficiently and degree reduce later. Let's not care about how this works. There's also a second way of how to do it, and I don't have time for this. However, let's get to numbers. We implemented this, and we got a blind signature scheme with, if you really take Fischling's approach and rebuild it in VOLE-in-the-head with Mayo, which is also currently in submission as an additional post-quantum signature, you get down to sign and verify times of way below 100 milliseconds and a blind signature size of 30 to 40 kilobytes. That's quite nice because in the post-quantum setting, the constructions we had before are blind signatures of that are like maybe of the same size, but where sign and verify times are more like 200 milliseconds. And then we got a different approach, which is which actually allows us to get the blind signature size down to 7.5 kilobytes with a sign and verify time well under 50 milliseconds. So just like outperforming all the state of the art of lattice-based blind signatures. And now the next question is, can this be turned into an anonymous credential scheme? Future work will show us. So in conclusion, VOLE-based ZK, well, it's a very simple proof system that gives you linear size proofs. It's very fast. VOLE-in-the-head makes it publicly verifiable. Requires some tricks to get it to work, but it's also not super complex theory-wise, engineering-wise a bit more. We turn this into a digital signature scheme, which is hopefully post-quantum secure, has much better performance than other signature schemes that rely on conservative assumptions like Sphinx Plus, while at the same time, so it has a better performance than these, while also having conservative security assumptions. And in the very end, I now talked a little bit about blind signatures from Mayo, where, well, we run a verifier for a signature scheme in a ZK proof, and it turns out it's not too bad. And with this, I'm open for questions. Thank you. If there's even time for any more questions.
Yeah, we have time. We can wrap it up whenever you're done.
I have a bunch of questions, but I don't want to front run anyone.
Oh, go ahead, Justin.
Okay, cool. I guess one question I have is, if you were to use Poseidon in FAEST.
Can you repeat the question? I think my internet connection just dropped for a second.
In FAEST, you currently use AES. What if you were to replace AES with Poseidon? Would you get significantly better performance numbers?
Nope, I don't think so. In particular, because Poseidon is usually defined over large fields. And there are not so many implementations of VOLE over large fields, VOLE-in-the-head over large fields available right now. However, what you can do, and which is fun, is you can instead replace AES with random linear equation, random quadratic equations, which is related to this Mayo assumptions. And it's still probably better than lattice assumptions, and it gives you signatures of around 3 kilobytes. There's actually a submission to NIST that does exactly that.
Got it. I mean, when you say Poseidon is not usually instantiated with small fields, how small is small? Because right now we're using Poseidon with 32-bit, actually 31-bit fields. And I believe you can even go lower than that.
Yeah, I know you can go lower than that. You could easily set it up in VOLE-in-the-head to run Poseidon and VOLE-in-the-head. We have just never done it. I have no idea what the efficiency would be, to be fair. Like, we care about AES because NIST, we use AES because NIST would find that compelling, because we use something as a one-way function that is well tested, while Poseidon is like, AES is standardized, Poseidon is not, right? That's why we used it.
Okay, understood. You mentioned you're in round 2 of the additional post-quantum signatures competition. Do you know how many rounds there are and when the final decision will be made?
No idea. I have really no idea. I'm also not the most optimistic for FAEST because I'm not sure if this is what NIST is actually looking for. What I think what NIST appreciates is that in comparison to other constructions, it is like what is running under the hood is really a full-blown ZK proof system. And this is why we got from FAEST to something like these blind signatures, POMFRIT blind signatures, so easily. Like it's all the same technique. There's not much that we had to add. So if NIST is actually looking to standardize something that can easily be turned into an anonymous credential, we'll probably hear back from them. That being said, do I have an idea how many rounds there are and how long things will take? No, I don't have any more information than you have as an outsider.
Got it. I guess in terms of security assumptions, when comparing to Sphinx Plus, for example, is it fair to say that in addition to introducing AES, you're also losing the opportunity to have security proofs in the standard model and kind of making use of the Fiat-Shamir heuristic, which also weakens security?
But don't you also need a random oracle in Sphinx Plus? If you hash your message to, I think at multiple points in the proof, you also need to consider the underlying hash function as a random oracle. Not in order to set up all these one-time signatures, but I think when you hash your message down to one of these paths, for example, I think there was also a step involved where you don't do Fiat-Shamir, that is correct, but you're assuming that the hash function is a random oracle as well. However, that being said, we do require likely more. Our security proofs are not as tight as Sphinx Plus, if I remember correctly. And we also need the security of AES in multiple ways. So it is, I would say, it's conservative security. It's more conservative than assuming new things, while Sphinx Plus is probably even more conservative than our construction.
Okay, got it. I guess another thing that I'm wondering is if you were able to somehow make AES snark friendly, like, is there maybe an opportunity to use these ideas to have a hash function based on AES, which is also snark friendly?
Yes. And if you look into our paper, we have a hash function called so AES as hash function, no, but if you replace shake with something else that is more friendly, we are in addition to the POMFRIT blind signatures that we do, we also have a construction where we replace shake with a hash function called rain, which you could look at as a version of kind of using the AES paradigm to construct a hash function on the super highest of levels. Like there's a lot more involved, but it is a hash function that is very, very friendly for MPC in the head-based constructions, I would say, but maybe also other for other snarks, for actual snarks. Like ours is of course not a snark.
Got it. So Rain, is that a hash function that you designed as part of FAEST, or is it a separate paper and team, I guess, behind it?
It is coming out of TU Graz. So Christian Rechberger and other people have been designing it already before. So we're not the first to use it. He's also behind Poseidon, right? So it's kind of the same team, I would say.
Okay, very nice. I guess one final question. Do you happen to be on Telegram by any chance? Because many of us at the Ethereum Foundation use Telegram.
No, you can find me on Signal and WhatsApp, but not on Telegram.
Okay, got it. Yeah, we're also on Signal. Cool. Thanks.
Do you have time for maybe a couple more questions?
Sure.
Yeah, I'm trying to understand what the proof size overhead is, like specifically going from the designated verifier setting, which I think in the binary field, it like more or less amortizes to 1 bit per multiplication. When you go into this VOLE-in-the-head paradigm, you said that there is some sort of like 13x overhead factor with that. Is that a constant factor? Like it's just a linear constant increase as the statement gets larger?
Yes. So in the following sense, in VOLE-based proof systems, you usually start out with some random voles, and you need to commit to the actual witness in the vole that you want to have. And in VOLE-in-the-head, if we work over F2, you have to send approximately 11 to 16 bits in order to commit to a single bit. Okay, so that's like for the witness input. Now, the thing I was trying to get across is that if you do with this, like thinking about degree reduction, not every outcome of a multiplication has to be committed to as well. So it's not that you pay 11 to 16 times input of the circuit plus number of multiplication gates. It really depends on your circuit topology what you have to pay, because if you can align things nicely, you can do a lot of multiplications before you have to reduce your degree again. And this is actually what we do in POMFRIT, in that we see, instead of, if you evaluate shake, you don't have to commit to all the rounds of shake that you do, because if you align the multiplication gates in a nice way, you can basically do 6 rounds together. Instead of communicating for every round, you just communicate for every 6th round, so to say. And so yes, you pay an overhead for these commitments, for like to commit to the witness, this 11 to 16. But you are also you are saving because you use VOLE-based proofs, which allow you to kind of squeeze the circuit evaluation together. Which then saves you in terms of proof size again, right? Because now you're sending less information to evaluate the circuit. That's where the interesting trade-off for voles are. There I have to say this trick of not paying for multiplications and doing degree reductions instead. It's also something that works for designated verifier VOLE-based proofs. So stuff like QuickSilver.
Right. Yeah, so I guess that would just be like a more efficient, like arithmetization.
Yeah.
Okay. Yeah. Speaking of QuickSilver, I'm not sure if I'm going to be able to recall this correctly, but it has some sort of like batched, like polynomial proof in it, where you can. Yeah. Are those techniques? Do those translate into this setting as well?
Not in ours. I remember that for Ant-Man, which is this batch paper, this batch extension of QuickSilver, there are works that translate this into a VOLE-in-the-head style setting, but somehow I missed ever reading the paper of how it works. And if any of the authors ever watches this video, I will be deeply ashamed.
Sounds good. I guess just one other one. I did ask you about this in email, but I just punted out here. So I guess mixed field, you've already kind of talked about this. So I guess like the efficiency kind of goes down when you start using larger fields. Is that a large blow up in proof size computation? Like what is the actual cost? Is your
it's actually, it's not, it is kind of, so the efficiency actually doesn't go down. It's actually quite the opposite. So when you go to larger fields, the interesting thing is like VOLE-in-the-head itself is super efficient for the mod 2 setting. And then there's a variant of VOLE-in-the-head that works very nicely for large prime fields, or even like mid-sized prime, even like 20 to 30 bits. However, and there actually the factor, the overhead that you pay is, even for VOLE-in-the-head, is more like a factor of 2 or 3, and not like 11 to 16. However, we never got around to implement the mod P version of VOLE-in-the-head, so I can't and without ever having played with with an actual implementation, I can't tell you much about how it performs.
Yeah, totally fair. Just curious, because yeah, often at least for digital identity, and particularly just like reusing like existing credentials, you're going to have like an ECDSA signature, but then you're also like, you would also not prefer to be in that field when you're trying to like validate like a JSON document or something like that. So the ideal case would be, you could just like arbitrarily switch between these fields, obviously with the cost associated with it, but wouldn't that be nice?
that would be nice. And if somebody finds me money for a PhD student and a PhD student, then this has been like high up on my to-do list for a long time. But yeah, without the actual men or women power to get this done, it's a bit difficult. But yeah, I am as curious as you are about this. In particular, how it compares with Longfellow ZK by Google.
Right, exactly.
Who do this, but using rather different techniques.
Looks like Justin's got another question.
Yeah, Carsten, just to give you a little bit of context on what we're doing with Ethereum. So, we want to move to post quantum security, and we're going to have lots of transactions. And for us, the number one scarce resource is bandwidth. So, moving from 64 bytes ECDSA to anything else is like very expensive. And basically the only solution that we know of is signature aggregation, where we have a SNOC that proves knowledge of multiple underlying signatures. And in order to get signature aggregation, the only solution that we know of that is practical is basically to have some reasonably SNOC-friendly signature scheme. For example, Sphinx, where you change SHA-256 with Poseidon. So for us in the Ethereum context, we're actually very comfortable with Poseidon, especially if it were to be shipped in, let's say, 2029. Poseidon would be 10 years old, heavily battle tested, and even today it's securing billions of dollars in the context of ZK rollups. And so this research into VOLE-in-the-head with the larger field sizes, maybe 31 bits, and using Poseidon is actually something that we would potentially find very interesting. And as an alternative to Sphinx, which is slightly smaller signatures. So I guess the reason why we still do care about signature size, even in the context of aggregation, is that there's the off-chain footprint and the on-chain footprint. So what goes on-chain is the SNOC, but we still have off-chain in the so-called mempool, like all of these large signatures that have to be gossiped. And
Sure.
We do have ideas, for example, mempool sharding and things like that, but it introduces complexities. And you mentioned that you yourself are very curious, and you've been looking for money and stuff like that. I guess, is this something that you would consider working with us, and like how much money would you want? And I guess
I have to say there, so if we talk particularly about snark friendliness, right? What you need to do in a snark in order to aggregate the signatures would be to evaluate the signature verification in the snark, right? If I understand you correctly.
Exactly.
Right. So this is actually not too bad in Sphinx Plus, because it's just evaluating this whole nice tree.
Exactly.
And verifying that you have some path in there, if I remember Sphinx Plus correctly. that is not so easy in FAEST or versions of FAEST, because the verification has to expand all of these trees to generate these VOLE correlations, and then apply the one-way function on all of this. Like, there's a lot of like these 500 microseconds. There's a lot of things going on computation-wise in order to verify the signature. And I honestly am not sure if throwing this into a snark is a better idea, because performance-wise, I mean, I agree that, like, gossiping-wise, you cut communication by a factor of 2, but snark-wise, you're going to be in trouble, simply because the verification circuit for Sphinx Plus or any version of Sphinx Plus is just so much simpler than for FAEST or VOLE-in-the-head-based proof systems. That's also why, like, the one thing where Sphinx Plus outperforms FAEST is that it has a much faster verification time, and that's actually where you usually want to use Sphinx Plus, right? If you want to, like, outside of the blockchain context, you want to use it where you need conservative security but don't care about signature size or prover runtime or signer runtime, which is like software signing or so, right? And from that perspective, I'm not so sure if I would try to wrap try to verify FAEST inside a ZK proof. It would be fun to see how it works out, but we haven't tried it, and I think Sphinx Plus would be much better candidate for that.
Okay, got it. Thank you for the honest assessment there.
Yeah,
I guess I'm curious. Go ahead.
That being said, if somebody ever tries it, I would be really curious about the results.
Yeah,
This is
same
a
here.
question I've also asked in the past as well. Is that mostly just the GGM tree, and you're having to do just like, yeah, okay.
Right, which is super efficient on your laptop or any kind of other device, because you have instructions for AES and I. But if you were to so all of these PRG calls are super efficient and can be neatly pipelined on a processor. But if you were to do all of the verifications of this kind of stuff in a snark, it's going to be a pain, because last time I checked, there are no AES or other PRG instructions for snarks that are super efficient. However, of course, you can replace AES with something else there, but it would still be the bottleneck.
I mean, if we replace AES with Poseidon 2, which I guess could be used as a PRG, we can prove on a laptop CPU 1 million Poseidon hashes per second. So, like, how many calls to the PRG are we talking about?
Good question, but you also want your output to be bit strings. Though you may not need that you don't need that for the mod P setting. So it is a good question. For the mod P, so for VOLE-in-the-head modular prime, modular large prime, it might actually not look as terrible. But I even having a pen and some paper, I can't do the back of the envelope at this point right now. Sorry. But
I mean, you mentioned
a few thousand calls for sure.
Okay, but right, because you mentioned the overhead being like 15 or whatever, and like I was thinking, okay, like the depth of your tree is like 15, so you have like 2 to the 15. So let's say 32,000 calls or whatever. Like, we can do that in a few milliseconds of prover time.
Yeah, but if you want to aggregate signatures, that's a lot of repeating that, right?
Yes, but it might still be relatively competitive. So for Sphinx Plus, we're talking about roughly 2,000 calls to Poseidon. So yeah, it depends on the constant there, like how many thousands.
Yeah. Also, I really don't know what the performance is if we use VOLE mod P, VOLE-in-the-head modulo primes for a signature scheme, because we have never tried that. So it would be interesting to see, but you might end up with signatures that are just that are even larger than the Sphinx Plus, which defeats the purpose.
Okay, got it. Well, if you are interested in
Poseidon?
Sorry?
Oh, sorry, you can finish that, Justin.
So I think I have high latency. I was just going to say, if you are interested in looking into this and you are looking for money, like, do feel free to knock on out.
Yeah. Thank you. I'll definitely keep that in mind. It sounds like that sounds like an interesting direction. I think I found the master project for a student.
All right. Well, this has been really great. Thanks so much for coming on, Carsten, and giving us a rundown on this. I think we probably call it there. Yeah.
Thank you for hosting me, and thank you for your time.